Finally, let's take a look at a complete numerical example. In this case, again, just like the Google PageRank lecture, we are constrained to a slide or a page, and therefore the examples do not represent the challenge of scale or sparsity. If you recall, scale and sparsity were the big challenges for Netflix price. So this only really serves the purpose of illustrating the 5 steps that we just outlined for neighborhood method. Here is our starting point. We are given, these are given constants, the rating information. Each entry of this big matrix R is RUI. And you see that this is 10 user by 5 movies. We label users 1 up to 10, and movies A up to E. And it is 80% filled. Okay, so 40 out of the 50 possible entries already actually known. This is again very atypical. Generally speaking, only about 1% instead of 80% of the entries are filled in a typical real data. But if we only have 1%, then we don't even have a single entry of known data in the training. Now, 10 of these are represented by bars. This means that rating simply does not exist for that user movie pair. And now we're going to say let's hide 10 out of the 40 known data as test data and use the remaining 30 as training data. So 30 samples for training and 10 to test our prediction. So somewhere arbitrary, let's just pick these circled 10 entries as test data. Okay, so we know, we just pretend we don't first and train with the remaining 30 points and see how we do on these 10 points. First of all, the very lazy R bar, in this case 3.83, in Netflix case 3.6. Alright, step number 1, baseline predictor. Let's construct the baseline predictor, which is R hat UI equals R bar 3.83 in this example, plus a bunch of biases for each user for each movie, and this holds for all the UI pairs. Okay, so we got how many? 10 of these parameters and 5 of these parameters. Got 15 parameters in this case for the baseline predictor. And we're going to pick the right baseline predictor parameters BU star BI stars by solving a least square problem. The least square problem is, as you'll recall, AB minus C L2 norm squared. We minimize this, and the solution is A transpose A times B star will be equal to A transpose C. So what are the A, B's, and C's? The B is easy. That's our 15 optimization variables. These parameters under training, B1 up to B10, and then BA up to BE. What about the matrix A and vector C? We simply construct those, and like what we did in the small 2 movie 1 user example before. In particular, this A matrix is gonna to be we have this 15 by 15, we have a 30 by 15 matrix. 30 because we have 30 training points starting from R1A to R10E. Okay, so basically all the points here that are not red circled are our training data. Okay, and we have therefore 30 equations and 15 variables corresponding to B1 up to BE. And the tables basically this matrix A is 0, 1 binary, is 0 everywhere unless we're talking about that particular user and particular movie. Say in this row, the first equation out of 30, we're talking about R1A as the training data. So we have to write a 1 where it corresponds to B1, the first position, and the 11th position, which is corresponding to the BA position. And the C vector is simply the known training data R1A down to R10E, subtracting the R bar. So now that we have defined A, B, and C, we can use this equation as the solution to this least squares problem, and the resulting solution BU vector star and BI vector star are just partially shown here. This is 10 entries, this is 5 entries. And then you can stick these back into the predictor here with the optimized BU, BI by training, and then you got the baseline predictor. Okay, that's step number 1. Now we can, for sanity check, verify. In the textbook you see all the entries, but here you can see indeed BU is quite positive, B1 is quite positive, and BA is also quite positive. That means user 1 tend to give high scores, and movie A is well liked. So just to make sure that's the case, indeed user 1 tend to give high scores, and movie 1 is well liked. Okay, a lot of 4s and 5s. So the bias computation is indeed making some sense. Step number 2 is the prediction on the baseline. So the baseline predictor, using the optimized BU, BI, and the average R bar, will give you this prediction. Okay, we call this R hat. If you look at this R hat, and remember, some of these are training data, some are test data. So these, for example, are the test data. Okay. And let's compare with the actual data, RUI, for say these 5 out of the 10. What do we have here? We have 5, 3, 2, 2, 5. Those are the actual RUIs that we were hiding from ourselves. Now that, let's see, 5, 3, 3, 2, 1. 5, 3, 2, 2, 5. 5, 3, 2, 2, 5. 2, 2, 5. Are they close to 5, 3, 2, 2, 5? Yeah, reasonable, I guess. 4.62. If you round up, it will be 5. But if you compute RMSE, then there is a difference of 0.38. 3.49 versus 3. This is getting a little off. Half a star off is quite off, actually. And if you, depending on how you treat this 3.45, you may round it to 4, and then you actually incur a significant error. And even without rounding, this difference of 0.49 is also quite big. This difference is huge. It's between 2 and 2.78. This difference is also big, and difference is quite small. So we pretty much get this quite right, this sort of reasonable, but these two predictions are kind of not that good. Okay. One way you can deal with this is to use regularization to avoid overfitting in the advanced material. But in general, baseline prediction doesn't leverage any collaborative filtering techniques of global structure, so we're not doing very well.